welcome to our channel, Mootechie. A special welcome to all the dairy technologists and students joining us. Today we're diving into the fascinating world of food and industrial microbiology, with a special focus on a key piece of equipment, the fermenter. Let's begin by understanding what a fermenter is. A fermenter is an apparatus that maintains the required optimal environmental conditions for the growth of industrially important microorganisms. It's used in large-scale fermentation processes for the commercial production of a wide range of products like antibiotics, enzymes, organic acids, and alcoholic beverages. The key function of an ideal fermenter is to provide a controlled environment for the growth of a pure or well-defined mixed culture of microorganisms to obtain the desired products. An ideal fermenter maintains optimal conditions throughout the entire process for the organisms, substrates, and additives, ensuring a quality end product. Saving energy and operating in a cost-effective way is very important for fermentation economics. You'll often hear the terms bioreactor and fermenter used interchangeably. While they are very similar, there is a minor difference. A bioreactor is typically used for the mass culture of plant and animal cells, while a fermenter is mainly used for microbial culture. However, their operational parameters and design engineering are largely identical. Parameters of an ideal fermenter. Now, what are the parameters of an ideal fermenter? A fermenter should facilitate the growth of a wide range of organisms capable of producing various products. It must prevent the entry of any unwanted microorganisms, providing an operation free from contamination. It needs to maintain a specific required temperature and provide adequate aeration and agitation. This meets the metabolic needs of the organisms and achieves mass and heat transfer without damaging them. It must control the pH of the culture and allow for constant monitoring of dissolved oxygen. It should also allow for the feeding of nutrient solutions and other supplements. Furthermore, a fermenter should provide access points for inoculating the seed culture and for taking samples during the process. It should reduce liquid loss through its cooling system and be capable of operating aseptically to meet containment regulations. The overall process should have low power consumption. The design should minimize labor during production and downstream operations like harvesting and cleaning. It should be suitable for a range of processes and have even internal surfaces, using welds instead of flange joints whenever possible. The fermenter should have identical geometry at different operational levels, meaning both smaller and larger vessels in a pilot plant should be similar. The material it's made from must be inert and withstand repeated steam sterilization. Adequate service provisions are also crucial. These include compressed sterile air, chilled and hot water, high-pressure steam, a reliable electricity supply, storage for media, monitoring equipment, maintenance facilities, and effluent treatment systems. General structure and components. Moving on, let's look at the general structure of a continuous stirred tank type bioreactor. Key components include an agitation system, feeding pump, the reactor tank itself, a submerged aerator, a system monitor, sensor probes, a thermal jacket for temperature control, and an outlet for effluent. A detailed diagram shows components like an exit gas cooler with a filter, a drive motor, probes for pH and dissolved oxygen, an inlet filter connected to a sparger, a head plate, reagent bottles for antifoam and base, a water jacket, a rotometer for measuring flow, and a control panel. Main parts and functions. Next, we'll explore the main parts of a fermenter and their functions. The impeller or agitator stirs the media continuously to prevent cells from settling and distributes oxygen. The sparger or aerator introduces sterile oxygen into the media in aerobic processes. Baffles act as vortex breakers, disrupting swirls for better mixing. The inlet air filter sterilizes air before it enters, while the exhaust air filter traps contaminants. A rotometer measures the flow rate of air or liquid. A pressure gauge monitors internal pressure. A temperature probe tracks changes in the medium's temperature, and a cooling jacket maintains it. A pH probe monitors acidity, a dissolved oxygen probe measures oxygen levels, a level probe checks the medium volume, and a foam probe detects foam. Acid and base are added to maintain the required pH. Fermenter design and materials. The vessel itself is designed to carry out the process under aseptic conditions with minimal labor. It has even internal surfaces and a similar geometry. Fermenter volumes vary greatly, from small laboratory models of 1 or 2 liters to pilot scale up to 1,000 liters and industrial scale fermenters that can hold several hundred liters. There are two main types based on scale: small scale laboratory fermenters and large scale industrial fermenters. Small scale laboratory fermenters are typically made of glass, like borosilicate battery jars. They have round or flat bottoms and a top flanged carrying. They are smooth, non-toxic, corrosion free, and can be sterilized in an autoclave. A big advantage is that you can see inside the vessel. Their diameter is usually more than 50 centimeters. Large-scale industrial fermenters are made of stainless steel, which is the most satisfactory material. These vessels can be sterilized in place, SIP, withstand high pressure and corrosion. Their corrosion resistance comes from a thin, continuous, non-porous hydrous film on the metal surface, stabilized by chromium. This property can be improved by adding elements like tungsten and silicone during manufacturing. Impeller/agitator. The impeller or agitator is mounted on a shaft through a bearing in the lid and driven by an external motor. It achieves several mixing objectives: bulk fluid and gas phase mixing, air dispersion, oxygen transfer, heat transfer, and suspension of solid particles to maintain a uniform environment. Common types include the disc turbine, vent disc, open turbine, and marine propeller. Sparger. The sparger is a pipe with minute holes that allows air under pressure to escape into the medium. Types include the porous sparger, made of sintered glass or ceramic, used in small non-agitated vessels, the orifice sparger, and the nozzle sparger, a single open pipe that creates steam for air bubbles and is less prone to blocking. Baffles. Baffles are metal strips attached perpendicular to the vessel wall. Usually 4 to 8 are used to prevent vortex formation and improve aeration. Their width is about 1/10 of the vessel diameter. A small gap between the baffle and the wall helps minimize microbial growth on the fermenter walls. Control systems. Temperature control is critical. Heat generated by mechanical agitation and microbial metabolism must be removed by a cooling system or added via internal coils controlled bath. pH control is equally essential, as microorganisms require specific pH levels. pH control sensors monitor and adjust the pH periodically. Feed ports are tubes or pipelines connected to a nutrient reservoir. They are used to add nutrients, acid, or alkali before and during fermentation. These ports are sterilized in place or off-site with steam. Valves. Flow regulation uses different valves. Safety valves protect pressurized pipes. Globe valves are for fully open or closed positions, not flow regulation. Butterfly valves are for large low-pressure pipes, but are not aseptic. Ball valves are suitable for aseptic conditions and can handle high temperatures and mycelial broths. Diaphragm valves are used for flow regulation. Shaft seal. The stirrer shaft must be sealed properly for long-term aseptic operation. Mechanical seals have a stationary and a rotating part pressed together by a spring, requiring lubricant. Packed gland seals use rings of asbestos around the shaft, which need periodic replacement. Magnetic drives use two magnets, one outside connected to the drive and one inside on the impeller shaft, to transfer motion without a physical seal. Fermenter versus bioreactor comparison. Feature: Fermenter Bioreactor. Typical size: small, up to 2 liters. Larger, from liters to cubic meters. Cell type: robust bacterial cells, microbial culture, sensitive mammalian cells, plant, animal culture. Growth/oxygen. Fast growth, high oxygen demand. Slow growth, low oxygen demand. Viral threat: no viral threat. Requires protection from viral contamination. Sterilization: fully sterilized with media inside, often sterilized, empty. A typical fermenter diagram includes a motor, steam inlets, a viewing port, an impeller, a cooling jacket, pH controllers, acid-base reservoirs, air filters, baffles, culture broth, a sparger for sterile air, and a harvest pipe. Classification and types of bioreactors. Bioreactors can be classified in several ways. 1. By the type of biocatalyst, free cells or immobilized cells. 2. By configuration, a tank or a column. 3. By how energy and air are input. 4. By hydrodynamics, meaning how well things are mixed. 5. By mode of operation, batch, continuous, or fed batch. Major types of bioreactors. Stirred tank reactors use mechanical impellers for mixing. Bubble column reactors are tall and use air alone for mixing. Airlift reactors, similar to bubble columns but contain an inner draft tube to improve circulation and oxygen transfer. Other types: fluidized bed reactors. Cells are immobilized on small particles that move with the fluid, creating a large surface area. Packed bed reactors. Cells are immobilized on large stationary particles, but these can suffer from blockages. Flocculated cell reactors retain cells by allowing them to clump together, mainly used in wastewater treatment. Moving on, we will see the stirred tank bioreactor, often abbreviated as STB. It is the choice for more than 70% of industrial work, even though it may not be the absolute best option for every application. STBs perform several key functions. These include homogenization, suspension of solids, dispersion of gas-liquid mixtures, aeration of the liquid, and heat exchange. The STB is equipped with baffles and a rotating stirrer attached either at the top or the bottom of the vessel. Baffles are usually flat vertical plates, and their width is about 1/10 of the vessel's diameter. Normally, 4 to 6 baffle plates are fitted to the inside walls to aid mixing and mass transfer. They do this by increasing turbulence, preventing vortex formation, and eliminating dead spaces. Inside the vessel, the impeller is connected to an external motor which drives the entire stirrer system. Next, we explore some important considerations for stirred tank bioreactors. The agitator assembly, including the seal, can be a potential route for contamination. To prevent this, the shaft must pass into the fermenter through a set of aseptic seals. There are specific regulations regarding the number and types of seals required. Typically, 2 or 3 seals are needed to minimize the risk of contaminating the fermenter. The effectiveness of the agitation depends on the design of the impeller blades, the speed of agitation, and the depth of the liquid. Most stirred tank reactors have a height to diameter aspect ratio of 3:1 or 4:1. These reactors must create high turbulence to maintain good transfer rates, but this also generates considerable shear force. Now let's look at the implications of that shear force. Many animal and plant cells are sensitive to shear, and excessive stirring can disrupt or even break these cells. In such cases, standard stirred tank reactors may be unsuitable without modification. For shear-sensitive cells, airlift reactors or supported biofilm reactors are often preferred. The key design decisions for an STR include the type, size, location, and number of impellers, as well as the size and location of the sparger. These factors determine the hydrodynamic pattern inside the reactor, which influences mixing times, mass and heat transfer coefficients, and shear rates. Because stirred tank reactors are commonly used for batch processes with only slight modifications, they are relatively simple in design and easier to operate. The industry still prefers stirred tanks because if contamination occurs or a substandard product is formed, the financial loss is minimal. In the following section, we examine the pros and cons of stirred tank bioreactors. Batch-operated stirred tanks generally have low volumetric productivity. Their downtimes can be quite long, and the unsteady state of fermentation can stress microbial cultures due to changing nutrient levels. Using a fed batch mode of operation can help eliminate this limitation. On the positive side, STBs offer excellent mixing and good mass transfer rates. Their operating cost is lower, and they can be used with a wide variety of microbial species. Using an STR with immobilized cells is not generally favored because the stirring causes attrition or wear and tear on the particles. However, by physically separating the mixing zone from the cell culturing zone, it is possible to successfully operate such a system. As we continue, we find another major type of bioreactor, the airlift bioreactor or ALB. Airlift bioreactors are classified as pneumatic reactors because they have no mechanical stirrers. Instead, they use the expansion of compressed gas to achieve mixing. The turbulence created by the flowing fluid ensures the liquid is mixed adequately. A key feature is the draft tube, which is provided in the central section of the reactor. When fluid, either air or liquid, is introduced, it causes an upward motion that creates a circulatory flow throughout the entire reactor. Even large airlift fermenters usually don't need internal cooling coils, because the rapid fluid movement allows a cooling jacket to provide sufficient heat transfer. The velocities of the air and liquid are relatively low, which means energy consumption is also low. Airlift bioreactors can be used for both free cells and immobilized cells. Coming up, we discuss the advantages of airlift bioreactors. There are very few reports on using ALBs specifically for metabolite production. Their main advantages include the elimination of attrition effects, which are commonly encountered in mechanically agitated reactors. They are ideally suited for aerobic cultures because their oxygen mass transfer coefficient is quite high compared to stirred tank reactors. They are also very easy to design since they have no moving parts or agitators. Sterilization is simpler for the same reason. Their energy requirement is very low, and they are generally low cost. A figure is included showing the gas and liquid flow pattern with an internal loop, illustrating the circulatory movement characteristic of these reactors. Let us go further and examine fluidized bed bioreactors, or FBB. These reactors have received increased attention in recent years due to their advantages over other reactor types. Most FBBs used in biological systems with cell biocatalysts are three-phase systems involving solid, liquid, and gas. They are generally operated in co-current upflow mode, with liquid as the continuous phase. Other configurations, like the inverse three-phase fluidized bed or gas-solid fluidized bed, are less common. Fluidization is usually achieved either by recirculating liquid from outside the reactor or by feeding gas directly into it. When working with immobilized enzymes, the system is typically a two-phase solid-liquid system, but using an aerobic biocatalyst requires introducing gas like air as a third phase. Following this, we notice the benefits of fluidized bed bioreactors. Compared to conventional mechanically stirred reactors, FBBs cause much less attrition or wearing down of solid particles. They can support a significantly higher concentration of biocatalyst and overcome the washout limitations common in free cell systems. When compared to packed bed reactors, FBBs can operate with much smaller particles without suffering from clogging, high liquid pressure drop, channeling, or bed compaction. This smaller particle size allows for higher mass transfer rates and better mixing. As a result, the volumetric productivity achieved in fluidized bed bioreactors is usually higher than in both stirred tank and packed bed bioreactors. A simple diagram is shown with a label indicating product out, representing the effluent stream from the reactor. A more detailed diagram labeled Figure 9.21 shows a skid-mounted fluidized bed process flow diagram. It includes components for biomass control, an expanded bed level, flow recycle, oxygen recycle, an equalization separation tank, an influent stream, a basket strainer, fluidization pumps, an adductor, a flow valve, a bubble contactor for oxygen and nutrients, the fluid bed reactor itself, and a final effluent stream. Now let's look at packed bed bioreactors. These are also called fixed bed bioreactors and are commonly used with attached biofilms, especially in wastewater engineering. Their use became more important after the potential of whole cell immobilization techniques was demonstrated. In these reactors, the immobilized biocatalyst is packed into a column, and nutrients are fed through from either the top or the bottom. One disadvantage is that the flow characteristics can change during operation due to alterations in the bed's porosity. When using soft gels like alginates or carrageenan, the bed often compacts during fermentation, leading to a high pressure drop across the bed. In the following section, we learn more about the challenges of packed bed bioreactors. In many cases, bed compaction can be so severe that the integrity of the gel particles is damaged. Additionally, channeling may occur due to turbulence within the bed. Although packed beds are considered a type of plug flow reactor where backmixing is absent, a slight amount of backmixing often happens in practice, which can change the fermentation characteristics. These reactors are generally used when the reaction rate is governed by substrate inhibition. They are widely used with immobilized cells. Several modifications, like tapered beds to reduce pressure drop, inclined beds, horizontal beds, and rotary horizontal reactors, have been tried with limited success. A diagram labeled Figure 9.18 illustrates a packed bed reactor used for treating groundwater contaminated with halogenated aliphatic hydrocarbons. The diagram shows a condenser, a rapid mix heated reactor set at 30 degrees Celsius, a centrifugal pump, raw groundwater inlet, a positive displacement pump, an air inlet, a co-mingling jet, a recycle flow line, the immobilized bed, and the reactor discharge. Next, we explore the bubble column fermenter. These reactors are used in many chemical, petrochemical, and biochemical industries. They are valued for their simple construction, easy maintenance, and low operating cost. They are cylindrical, with a common height-to-diameter ratio of 4:6. At the base of the column, air or gas is introduced through perforated pipes, plates, or a metal microporous sparger. The flow rate of the air or gas is carefully maintained to ensure proper oxygen transfer and mixing. Perforated plates are sometimes attached inside the fermenter to improve the reactor's performance. A simple diagram shows the key parts: a gas outlet at the top, a sparger at the bottom, bubbles rising in the column, and a gas inlet. Coming up, we discuss photobioreactors. Although many models are planned, only a few can effectively utilize biomass from algae. The main application of photobioreactors is in photosynthetic processes, such as growing vegetable biomass or microalgae under controlled conditions. They range from laboratory to industrial scale and are classified into types like closed photobioreactors, open ponds, flat plate reactors, horizontal or serpentine tubular airlift reactors, and inclined tubular photobioreactors. The development of more complex microalgae cultivation methods, which offer higher production value, is made possible by different types of closed photobioreactors used outdoors. Laboratory-scale photobioreactors are typically artificially illuminated using fluorescent or other types of lamps. Some specific types of photobioreactors include open ponds, flat plate, tubular, bubble column, airlift column, helical tubular, conical, torus, stirred tank, and seaweed-type reactors. According to researchers Ugwu and others, the main disadvantage limiting their practical application in mass algal cultures is the challenge of mass transfer, which is crucial for processing large volumes of algae. Algal biomass is mainly used in water treatment, aquaculture, the production of fine chemicals and dietary supplements, and for the biosorption of heavy metals and carbon dioxide fixation. Finally, let us examine membrane bioreactors or MBRs. These have been in use since the 1990s. They basically combine a traditional biological treatment system with membrane filtration. This results in the removal of organic matter, suspended solids, and high levels of nutrients. In an MBR system, the membranes are submerged directly in the aerated biological reactor. The pore size of these membranes is very small, ranging from 0.035 microns to 0.4 microns. After the mid-1990s, with the development of the submerged MBR system, their use expanded widely and continues to grow rapidly in both research and commercial applications. Several variations of MBR systems have evolved, and they are now widely used for treating wastewater from various sources. In the coming years, it is expected that MBR systems will increase in capacity and broaden their application area. However, a major obstacle to the widespread use of MBRs is membrane fouling. Furthermore, for large-scale use in wastewater treatment to become more common, there will need to be a significant decrease in the price of the membranes. A figure is referenced, figure 5.13, which shows a diagram of the membrane bioreactor method. Thank you for listening to this comprehensive overview of fermenters and bioreactors. We hope this session has been informative and helpful for your studies and work in dairy technology and related fields. The key takeaway is understanding how these vital vessels are designed and controlled to harness the power of microorganisms for industry. Thank you. See you in the next class.